Our next speaker is Bogna Jaszczak, who will tell us about modeling trail running, a very interesting subject.
Good afternoon. So today I would like to talk about, as you can see, modeling trail running. So at first I would like to explain a bit what do we understand by trail running, then discuss a bit the subject of Keller's model with some modifications, and as a, let's say, bonus, a fragment about predicting the finish time. So what do we understand by the trail running? It is basically the name for all the running events that take place on different places, different types of natural off-road terrain. So it can be forest, it can be the mountains, it can be like a desert even. And what is important, there is like no limit on the distance, there is no limit on elevation gain, just about competing in like the natural terrain. And if we want to talk about modeling the running, the most natural, let's say, starting point is the Keller model, which was introduced in 1973. And even though this model is quite simple, Keller managed to reproduce the world records from 100 meters up to 10 kilometers with quite good accuracy. And like the main equations that appear there are the equation of motion. So here we have like just the basic second Newton law. So the runner is using some propulsive force to move forward. And there is like this resistive term. We are going to use like this linear one, so V divided by tau, in a similar manner as Keller did. And there is like this gravitational factor, which appears in case of some slope. And of course, if the root is flat, then it is equal to 0. And the second equation is equation of energy. So we have like the sigma value, which is like an energetic equivalent of VO2. And basically what we understand by this equation is that if the runner, work done by the runner, so this F times V is greater than the sigma, then we would have like a decrease in the energy level. So what is our problem? We want to find such a velocity profile that maximizes the area under the velocity curve. So in general, we want to it is like it was shown by Aftalion and Bonas, we have the reference in the next slide, that we can treat the problems of maximize the distance in given time t and minimize time t to cover the distance d in a similar way, as they are equivalent in terms of finding the optimal strategy. And we have like two constraints. First is regarding our, let's say, control variable. So it needs to be between 0 and some maximal force, capital F. And of course, the energy level cannot be negative. And as it was shown by Aftalion and Bonas, actually, it is quite interesting that over 40 years, there was like no proper proof of this solution. It was usually that the hypothesis about those three, let's say, arcs was stated at the beginning, and it was like matched to this hypothesis. And they for the first time proved that it is the actual solution of this problem. So we have at first the maximal force arc. So the runner is using, and the maximal force is able to use. Then we have the singular arc, which appears because if we write the Hamiltonian, then this constant, control variable appears like linear in there. And it is the arc where the bound constraints are not active. And at the end, we have the zero energy arc, so that this energy is equal to 0 over the whole interval. And if we look at the solution for this classic Keller's model, we can see that they are not like, let's say, very interesting. At first, we have this acceleration phase using this maximal force. Then there is like almost for the whole race, like almost constant velocity and some deceleration at the end. And so, well, and it works quite okay for like shorter distances, but we would like to, of course, modify this model to make it more matching for the longer ones. So first improvement we want to add is the nutrition, as providing some exogenous carbohydrates during the race is quite a natural part of running the long distances, as it has been shown in many researches that providing the carbohydrates during the exercise increases exercise capacity and performance. And to model this, we are using the results from this cited paper, which describes how many grams of carbohydrates is our body able to convert into an energy while the exercise is taking part. And we can describe this curve with pretty nice, simple logistic differential equation. Here, this delta is this maximal value of exogenous carbohydrates oxidation rate. And the final form is like this. Is that for this equation of energy, we have the nutrition term, which is like recalculated from these grams of carbohydrates to joules and divided by body mass to match the units. And well, if it comes to the strict proof, it's still in progress, but I can put some spoilers because we would have also like this maximal force arc, similar as in the basic Taylor's model. So in both cases, we have such equation of for velocity. So it's like this increasing function. However, we need to remember that the second constraint needs to hold, so that the energy, of course, cannot be negative. So we are left with such inequality. And here is like quite important remark, because we can notice that if this element, like here, if the sigma divided by f to the second power and divided by tau is greater than 1, it would mean that the runner can run using the maximal force infinitely, which is unfortunately not the case. So there needs to exist some critical time after which the runner needs to reduce the thrust. And we can see it is like expressed in time divided by tau to have like some linear dependencies, so that this critical time is a bit bigger when we consider the nutrition, and this TC is like the point of intersection with the green line. And we can even find the formulas, so it's like the exact one for the case of nutrition, without nutrition, sorry. And in case of nutrition, we need to use some linear approximation. However, we can notice, of course, that this function behaves like almost like linear for such parameters. And we can have like the approximated value of this TC. And if it comes to this part, even though, of course, this nutrition element increases this TC value a bit, it is like really small difference. It is something about a 10th part of the second. So like there is no real impact. And it is fine because, of course, for the sprints, we don't like consider this nutrition. And if it comes to the values that come from these formulas, for example, when I set them to like my physiological parameters, it was like I can run using this maximal force around 36.5 seconds. And so it would mean I would run, I could use this maximal force running around like 200 meters. And we also have like the zero energy arc. And in the case without nutrition, we have such square root. And this function can be increasing, decreasing, or constant, depending on this C constant, so from this initial value. And for the case with nutrition, we have like this nice non-trivial result, because it is like hypergeometric function. And it can also like behave in a bit different way, but only like this initial phase. So you can, at the beginning, increase the speed, decrease the speed. However, then it kind of stabilizes and starts to slightly increase. And we can see this comparing the strategies. So we can see that with the nutrition, we have also like this almost constant velocity phase. However, then we have like this slightly increasing velocity. And it is the case for the 20 kilometers. However, when we consider the shorter race, for example, like 5 kilometers, we can see that this difference is much smaller. And we have also like this strategy very similar to the basic one. It's basically almost the same. So also like almost constant velocity throughout the most of the race, and then this deceleration at the end. And we are kind of pleased with such solution, because as in real life, it would mean that for the shorter distances, like 5 kilometers, again, this nutrition has really low impact, but this impact would increase during the longer ones. But of course, we need to remember that this increased value of exogenous carbohydrates oxidation rate is not increasing because we are, well, eating more bananas, so we are getting stronger till the end of the race, but it is rather our body response to the fatigue. So we need to add this fatigue. And there are a few suggestions in the literature. For example, again, Aftalion and Bonans propose to use such function, meaning that if this energy level drops below some critical level, there is also a drop, like a jump actually, to the lower value. And otherwise, it is like this starting value of sigma. And it worked fine for this 1500 meters that they considered. But in case of longer races, it was like not working really well because the differences in a, for example, in a 20 kilometers race were about like 6 seconds. So almost like no difference. So maybe the better idea would be to follow the idea of Woodside, so that to notice that this fatigue can be cumulative, first of all, and the second of all, that is proportional to the work done by the runner. And in this case, we can like, and again, add to this energy equation, this fatigue term, but we can go further. Because there was a research done by Minetti, who ran a series of experiments, which were about walking and running at the motor-driven treadmill. And there was a changing slope and changing velocity. And he measured a lot of parameters like VO2, like heart rate, lactate, and so on, to state what is the metabolic cost of running. And it turned out that it is like in a shape, let's say, of parabola. And well, his first remark was that in the same slope, there is no difference in metabolic cost of running for different velocities. However, it depends, this metabolic cost of running depends on the slope. And here is like important observation. So that, of course, when we are going uphill, the steeper the slope, of course, the higher metabolic cost of running. And then for like, let's say, steeper downhill slopes, at first it is getting easier for us to run, but then it increases again. And it is quite important because, for example, it does not appear in this standard Keller's modeling, because having like just the sign, it would mean that the steeper the slope, the easier it is for us to run downhill. And we can define this analogously because this CR has the same units as our propulsive force, and define this fatigue in such way. And like finishing this flat root part, and we can see the comparison. So both for modeling the fatigue with Minetti and Woodside, we can see that there is like this slight deceleration throughout most of the race and acceleration in the final kilometers. And it's kind of fine because it is what we mostly observe during the runs. Rather, the runner, due to probably some psychological results, prefer to accelerate at the end to like, have a better position at the finish line. But we can also look at some example varying slope routes. And here we can see that, well, of course, the lower the slope, the higher the velocity. But in case of Minetti, you can see that, and there is this difference of like this highly increasing metabolic cost of running in case of the steeper slopes. So this velocity is lower, starting from the significantly lower, starting from the points after this highest slope moment. And it is even more visible if we take a look at this strictly uphill race. So there are no values of the slope below 0. And here we can see that even though at the beginning those strategies are quite similar, then due to this fatigue accumulated on the uphill parts, this Minetti, this velocity for the Minetti case is much lower. And we can, of course, use those models to, for example, reevaluate our own races. So here is the example of Bogna race. It is like an uphill race that has like 5 kilometers and 500 meters of elevation gain. So looking at some, I don't know, conclusions, I could notice that, for example, probably I started with a bit too high velocity, and in general, based on those strategies, I should rather focus on keeping maybe not constant, but slightly decreasing velocity, but definitely not to vary this velocities so much depending on the slope. And this promised bonus, let's say, I was curious if the results of the job of Minetti could be useful to predicting the finish time, because in their paper, they also did some kind of, let's say, prediction of finish time, but only on strictly uphill or strictly downhill races. And the idea was that we can assume that as the race is quite long, then we would use mostly our aerobic energy, let's say. And probably, as it's like the competition, the highest available for us. And so in each point of the route, actually on some segments, let's say, we calculate the velocity. So we compare like the sigma value to this metabolic cost of running. So I mean this energy expended. So this CR times V. And we have some, let's say, correction factor. Because what Minetti realized was that even though based on the experiments on the treadmill seemed to be okay, it turned out that in the real life, during the downhill races, the results were much worse than in the predicted ones. And it was like, I don't know, probably some 30% or something like this. And based on that, we can calculate the final time. But what is important, we don't treat the sigma as a constant, but we have like two factors that impact this value. It is also like suggested in this paper. So first we have the race duration. So this capital T is like this, let's say, expected race duration. And we have the impact of altitude, because the higher we are above the sea level, and let's say less amount of oxygen is available for us to convert it into an energy. And finally we obtain this value of sigma. And well, I find this value of this PA, it was about 0.14 in my case, to compare to, let's say, predict the finish time for the races I took part in. And actually it turned out that this very simple method works quite good, because most of the results have an error around like 2%, definitely lower than 5%, with one exception, which was Piekło-Czantory race. But as the name suggests, it's like the real hell. And it was like also really hard conditions if it comes to the weather, if it comes to the terrain. So it was naturally taking a bit longer than suggested. But not to be like, okay, it worked for you, it won't work for everyone. I checked also the results for with the same, let's say, correction factor for different values of sigma. So let's say different levels of runners. So this 30 corresponds to like the elite runners. This 22 is like the real good amateur, and this 13 is like the amateur. And actually the results are also in agreement with the race and the records of such routes, because, for example, the current record of Bogna Jaszczak is 25 minutes and 7 seconds, and similarly in Golden Mountains Trail the route record is around 2.5 hours. And for those small local races like Valigura Run Cross, or for example this Piekło-Czantory, the results are really similar if it comes to the route records to those values of sigma equal to 22. So even though this method is simple and this has like incredibly low amount of input parameters, it works pretty well. And what I would like to add here is like, I'm not even so interested in such cases of predicting the finish time about, okay, I would like to know exactly to the second what would be my finish time, but something around, okay, from minus 15 minutes to plus 15 minutes to at least, I don't know, plan this nutrition strategy. So I don't know how many snacks should I take with me to have like enough to provide some energy during the race, or for example, when I should tell my family, okay, go to the finish line because I would finish soon. It is like pretty nice too and worked surprisingly well. And thanks for attention.